Hi, my presentation today is containing pieces of work that is related to visualization, but not in the same way as Fernando's work. It is related to how we can model in a visual way in order to achieve something. So it's not the end product, it is a means to get something out of it. So I'm gonna go through several things that we did in a variety of environments so that to give you an idea of what it is that we're working on. So the work is representing three centers, actually three people from three different centers, all at George Mason University. What I would like to mention is a little bit of our prior work on spatiotemporal modeling, talk about geosensor networks as opposed to sensor networks alone, discuss application domains where we have been involved in, talk a little bit about event monitoring, and discuss current research. Now, if starting the discussion on spatiotemporal modeling, what I'm showing you here is the outline of a hurricane as it evolves over time. So it slices of time, temporal slices of an event that has a spatial content and also a temporal content which represents its evolution. So it's a hurricane developing and we see how it looked like in the spatial domain at various temporal instances in a sequence. Now, this is one natural phenomenon that is worth investigating, studying, predicting maybe in order to have answers to questions that could affect our everyday lives. So how can we take this phenomenon and convert it into a model that is visual, but not a visual, just visual, that it has aspects that can create an abstract version of it that can be used later on for discovering trends and qualities. So we devised the spatiotemporal helix, which is what you're looking at here. If this is space, X and Y, and this is time, this is a way of representing a phenomenon that evolves over time in a certain way. So we have the nodes, which represent location in space, time, and an attribute that is of interest to us. In this particular case, it might be a lake and the changes that have occurred when heavy rains fell. And the prongs refer to what is happening to the attribute that we are interested in. In this case, the shape of this particular lake. Is it contracting? Is it expanding? And what are the angles of that? Now, this is a model that can be used to visualize or convert a spatiotemporal phenomenon into something that can be used to study similarities, for instance, between maybe related, maybe unrelated things. Now, this is a data set that we used in the past. It is sign language. So these are two words, and we plotted in space and time the movement of the hands of the person who was expressing in sign language these two words. So you see in this particular case the word Norway and the word cold. So what we use the spatiotemporal helix to assess similarity between two or three or various people expressing the same words. And you see it came back in a hierarchical manner and gave us better matches, less good matches, and so on. So we have been using this to find similarities among phenomena or phenomena that can be visualized in a spatiotemporal manner, modeled, I should say, or even words or other things that have a space and time component to them. Now, let's talk a little bit about how this work is related to sensor networks and environments where sensors are embedded into them. Now, I don't have to repeat all those things that all the speakers before me mentioned, that we are moving, that we are moving away from the static paradigm of doing things. We have Wi-Fi devices, laptops, mobile, wearable, everything. Now, the important part to remember here is that fixed infrastructure is expensive to implement in a dense and sophisticated manner. It's getting better, but it's not yet there. But also there is a danger in a situation of emergency of being destroyed. So we go into ad hoc networks, which can be mobile and which are easily deployable. And this is because we want to avoid the disadvantages of the fixed infrastructure. Now, data mobility and even node mobility, if we're talking about sensor networks, are two things which are of interest to a variety of application domains or sectors. You can see in health, disaster recovery, military, commercial applications. So this is not something that is coming out of a particular need, but it can address the needs of a variety of applications. Now, geosensor networks, when we talk about geosensor networks, we are referring to primarily hierarchical organizations of sensors, and we are hoping to have environments where sensors are collaborating in network. Now, the monitor in this particular case is aware of the geographic space, hence the geo term, and it's still focusing on phenomena, but we are interested in the world around the phenomena as they evolve. Now, the geospatial component of the information is very important in this case with respect to the content and the analysis as well. So we are, in terms of the research and in terms of what is expected, we are moving away from just spatial to spatial-temporal. And this is not new, obviously. I mean, this is something that has been going on for a while. But it is much more prominent nowadays that we have the capabilities of creating ad hoc and efficient networks. Now, I'm going to talk about a little bit about the domain that we haven't heard anything about so far, even though it is a domain that relies a lot on these technologies and that a lot of things are happening. And this is the surveillance domain. Now, as you can tell here, I included the word distributed surveillance, and this is a subsection of the general domain. So what I'm referring to is video-based surveillance, in which case our sensors are what it is that we are collecting are video feeds and which are distributed. Now, what we are doing in this is obviously tracking objects. Now, these objects can be physical objects, can be phenomena, can be humans, can be anything. Now, we're interested, I mean, the thing that is happening in these environments is that information is linked across feeds. It's not a straightforward issue to have feeds from a variety of sensors or cameras in this case and integrate them in a way that we can identify what is of interest to us in terms of phenomena, activities, and respond to queries, because the ultimate goal of this is to be able to answer queries with respect to whether something is happening or whether something is suspicious or whether action is needed. Now, obviously, the end product is the communication of the captured information. Now, how do we go from video feeds to spatial-temporal queries? Obviously, I'm not going to take you through all this work because this is really a big process, but the idea is that we have a variety of feeds, that all these feeds are combined, that tracks, we have the interesting aspects tracked, linked, modeled, and in space and time, and the results can be shown a variety of ways. In our domain, we are using obviously GIS environments, or we can use annotated video frames. Now, what is the problem that we are facing with respect to our work in the spatial-temporal modeling arena is that we have the helixes, which I showed you before, that we can use for, as I mentioned many times already, for a variety of phenomena. But coming back to a phenomenon that is dynamic and rapidly evolving, just as, for instance, the atmospheric releases in a metropolitan area, can it be used? And if yes, how? Now, in this case, we have a sensor network, which is placed on the ground, and it collects ground concentrations. So the objective here is, and I emphasize the word real time, is to identify where we could have potential contamination areas before it happens. Now, I'm not saying before toxic gases are released, because we don't know that. But after toxic gases are released and before they reach certain areas that contamination can occur, can we stop it? So our objective is to identify in real time potential contamination areas. When we have indications of toxic releases happening and being picked up by our sensors, to facilitate this and make it happen in real time, we have been using library of events. Now, the methodology that we followed here is that we have obviously the model of how a gas or a toxic substance propagates in the atmosphere is not a simple one. There are a lot of parameters that can affect it. So what happened was we talked and worked with application domain experts, and we simulated hundreds of types of releases using different atmospheric conditions. So we have, in terms of winds and density and atmospheric models and all those things. We built a library of these releases, and we have simulated how these models would affect certain areas of interest. Now, when a new release is identified, then it is compared to the library, and the contamination area is identified based on that. Now, what are the challenges that we are facing? We are facing the challenge of, having atmospheric conditions which are not 100% predictable all the time, so they're variable. We have ground measurements which are collected by a sensor network which might not be optimum. There might be sparse sensors. There might be only a few of them operating, and also one more complicating factor is that the release time is unknown for the ground measurements, because we have a sensor picking up on a release, but we don't know whether this release has happened yesterday, has reached the sensor today, when it happened, and this is really a complicating factor. Now, this is a way to use actually our approach to reconstruct how a toxic cloud moved over an area and how it looks. So you see it started from here, and the nodes represent where it was over time. And this is a last instance, or we picked this instance, but there is information about our simulation of how it is with respect to density and composition of gases at every one of these instances. Now, this is how all these phases are, starting from how it started and what our sensors picked up here, and how it moved, and where it is right now. Now, this is a way to model, but this is also a way to predict if we have additional information, which we do. So the idea is not only to visualize after the fact, but also to use a potential way of reconstructing how it will be moving and how it will be looking like in order to predict and protect. Now, the event helix in this particular situation has been extended to include not only the nodes and the prongs here, but also with color, which you cannot see very clearly here, it looks better on my monitor, represent the ground concentration and how this has been changing over time. Now, the experiments that we have performed in this particular situation, which is a problem that we found with potential huge interest, is we have had 500 releases simulated using a Gaussian model, and we used a variety of atmospheric conditions like speed of wind, direction, and velocity. Now, we use cross-correlation for each of these experiments. And the interesting part here was to use not always the 100% of what we know, but varying percentages of that, because you don't know how much you will know. So we started increasing the length from 10% up to 100%. Now, the assumptions in this is that the release time is unknown, unfortunately. So every portion of the monitor release is compared not only to a specific part of each release, but the whole length of our library simulations and information. And the wind field varies over time, but overall, we assume that it is constant over the entire domain. Now, this is output of the exam of our experiments. Now, what we have here is the number of helixes that we have available, and what we have here is how many of those. These lines represent how much of each release we have used. Now, if you see the 10% usage gave back a lot of potential matches. And the more we have in our library, the more matches it found, because it's only a small piece of that. But still, you can use even a small piece to narrow down the field. Then it still gives you, goes from hundreds to 10, let's say, or 20, which is better than not having that. But if we go into the 90% representation, you see that, even if you have 250 helixes to compare, you still come back with one match. And this is because you have almost all of it in it. So this is the results that we have achieved with this. Is just an indication of this is a good way of narrowing down what you have, and the more you know, the better your results are going to be. Now, there are some computational challenges that we want to solve in order to create a smarter network environment. Now, in this case, I'm showing you that, let's say we have a sensor network and we have sensors which sense different things, for instance. But the interesting part here is temperature, here is fire, here is nuclear. So the interesting part here is not just to communicate as single feeds or multiple feeds to analysts, is to have a way of moving and densify on request our sensor. So the sensor itself does not remain static, but if, given what we know, the sensor itself can move and or expand its area of sensing. Now, this is really an area that we are working on, and there are a lot of challenges to deal with. Now, in the interest of time, I'm not going to go into all the details, but what we are doing is that we have the processing nodes which are receiving and analyzing data, not just getting the data. We have sensors which are both routing and collecting data as well, and also the sensors. One issue that is a potential issue of trouble is that sensors measure the aggregate, which stems from multiple events. And this is a major research issue for us, how to separate if a sensor shows an increase in temperature, if this is because something happened in this particular sensor, or is because two phenomena have happened, like a fire plus a heat wave plus, and a gas that is increasing temperature. So this is the difficult part here, the readings that we get and the information that we get to separate it into where it's coming from. And here is an example of samples. If you have a window and you have some events that are contributing to a sensing device increased readings, and you can see that in this simulated example, there are a lot of events that contribute to that. So what we want to do is we want to analyze that, and this is what we're working towards, and separating which indications are coming from which parameters. Now, we have developed an approach which is based on fingerprints of events, and what happens, and as I said, I'm not going to go into all the details, but it still goes back to the same approach. We have a library of events. We construct the fingerprints, and these fingerprints go back to the library. They are matched, and recursively, and then what happens is that the highest scoring fingerprint event is removed from the aggregate data. This process is repeated until we are left with each one of these things individually. There are still limitations to it and our approach when we're working on that, but it is a very promising one for decoupling event and signals, which is a major issue in this process. Now, coming back to the contaminant releases, this is an example of this is from the Bosporus. This is a release, atmospheric contamination, and it is projected onto a risk map, and this is an automatic production of this, which shows how expected some contamination was based on former models, and how something is events that have occurred which have triggered red alert with respect to this particular release. Now, our current work focuses not only on forward simulation, which is how something evolves, but also backward simulation, which means that we want to detect the sources of the releases. It is not enough to know that something is happening. We have to know where it is coming from and go back and correct that. Now, one additional thing that we are working on, and this it applies to both the surveillance and the other applications I mentioned, is the event-based algebra. In this case, we are working on, and we have approaches which say what if an event happens at a particular location at a specific time, and there is another event that has happened at a different location at a different time. Can this be used to predict that a third event will happen at another location at a different temporal instance? So, for instance, if there is a gas emission that is reaching an area and there are certain conditions in this area, do we have a medical emergency? Is there a dyspnea? If there is wind going in this, how are these things all related to come back to something that occurs and which we could be protecting people from? And a last thing is the spatiotemporal multimodal triangulation, which is a work that we are working on with linguists from Brandeis. And in this case, we augment what we have from video feeds and image feeds. Like, for instance, we have various images which can pinpoint locations of people or phenomena of interest. But we also have other types of information, text information, verbal information, and this can be used to predict things. Like, for instance, in this particular example, this person has seen a person stopped at the newsstand and then walking down the street. So what does that mean? It means that this person could be in this area. Now, another person, from a different point of view, is looking at the same person coming towards. So it means that it could be in this area. Now, the intersection of the two means that this person could be somewhere here. Now, this is a very simplistic example, but this is ongoing work, and it's really very interesting. Our goal here is to build on our previous work on positional metrics, which is expressing positions relative to the scene, and distance metrics, which is expressing relative distances among objects in the scene, to create projective relationships, which will tell us how ground level view and bird's eye view can be related. Our goal here, and this is the interesting part I want to close my presentation with, is to really create different kind of sensing in which humans, with their discussions, with their text, with their behavior, become sensors, and positioning information, which is of interest to us as people dealing with geographic information, can be derived from their descriptions. Now, as a summary, what I try to summarize today is our helix, which is an ongoing work. We have application environments where it's being used, and this is just an example. A specific problem I showed you is of particular interest to us. And the research issues that we are working on is multiple events, integration in algebra, and interaction with the environment. And with that, I'm going to close and repeat that I'll be more than glad to hear from you if you have questions or comments. I apologize for not giving you a more colorful presentation, but this is really work that is happening behind the scenes of our applications. And we are really very interested in hearing comments in terms of potential application domains, in addition to the ones that I mentioned. Now, this is a combination of work between 2 departments and 3 centers. Now, don't expect that all these people involved in this are parts of this work. There's 3 people working on that, plus our graduate students. So thank you very much.